Hello everyone. So in the last class, we were looking at different scales in terms of the Navier-Stokes equations, right? We wanted to look at the different length scales in turbulent flows, especially because turbulent flows is made up of a wide range of length scales. So we started by looking at the Navier-Stokes equations, and we did sort of a scale analysis of these equations briefly earlier. But just to repeat what I was finishing off from last class, we have the inertia term on the left hand side. Again, the unsteady term is neglected. I have a pressure gradient term, so let's keep that aside, the pressure gradient term. And then I have the viscous term on the right hand side, which is the second term on the right hand side. And if I do a dimensional analysis of each term, order of magnitude, the inertia term becomes u squared over L, as I have written here. And then on the right hand side, I have mu u over L squared on the right hand side. So if I just divide these two terms, right, if I divide inertia by viscous, I'm supposed to get Reynolds number, and that is indeed what I get, where I get UL over nu. Okay. Now that is all good, but then when you think about high Reynolds number, right, a Reynolds number is the ratio of inertia over viscous. So at high Reynolds number, we tend to think that the viscous effects are negligible. So they can be neglected possibly. However, the boundary conditions and initial conditions of the flow might not allow us to do that. Okay. So for example, flow over a flat plate, boundary layer, you have the no slip condition that has to be satisfied. In fact, any flow that involves a solid surface, there is a no slip condition that has to be satisfied. If you completely neglect viscosity or viscous effects in general, then the no slip condition cannot be satisfied. Then the boundary layer does not exist in the first place. So that takes us into a bit of a conundrum, like what do we do here, right? But you can solve this problem by thinking of the viscous effects acting at a different length scale. And that's the benefit of, we have a turbulent flow here. There is a wide range of length scales. So every term in the Navier-Stokes equations or every effect physically might not be acting on the same length scales. For instance, in this case, the viscous effects are acting on the small length scales, right? So these can survive, the viscous terms can survive at high Reynolds number only by choosing some kind of a new length scale. And because you have a different length scale in turbulent flow, you can choose a new length scale L such that the viscous terms are of the same order of magnitude as the inertia term, which is what I have written here. So you see, this is the inertia term and this is the viscous term, I and V. Okay, I'm just calling it I and V. And you will see that I used a different length scale in both of these. So on the left hand side, I used L, capital L, and on the right hand side, I have used small l, okay, indicating the fact that the viscous effects are dominant at the small scales. They are neglected or they are negligible at the large scales. Yes, that is still true, but they are dominant at the small scales. So this viscous length scale small l, okay, you can relate it. Now what we are trying to say is, before I go to the equation number 15, I want to point out that what we are saying is the inertia and the viscous terms are of the same order of magnitude as long as you choose the correct length scale for the corresponding terms. Now from relationship 14, if you take a ratio of small l over capital L, you get nu over ul to the half. That's what you get, right? Because you have a small l squared here, you have a u squared here. So all of that results in nu over ul to the half. It's easily obtainable. Now nu over ul is 1 over Re or Re to the negative 1, in which case this turns out to be Re to the minus half. So this gives you an idea that viscous length scale as a ratio, so viscous length scale in comparison to the large length scale, capital L, is Re to the negative half. That means if the Reynolds number is really large, which it is for a turbulent flow, then the gap, the difference between small l and capital L is large as well. Okay, it varies as Re to the negative half. So that gives you an idea. So that is a viscous length scale in comparison to the large length scale, correct? So we can call this viscous length scale a transverse length scale. Okay, in one way it represents the thickness of the boundary layer or the width of the boundary layer because it is related to the molecular diffusion of momentum deficit across the flow. Think about that. This viscous length scale comes from the scales at which the viscous effects are more dominant, which is near the solid surface, near the plate. So that means it is related to the molecular diffusion, isn't it? It is related to the viscous diffusion or molecular diffusion of momentum, because we are talking about the Navier-Stokes equations. So obviously it is a diffusion of momentum, and it is a diffusion of momentum deficit across the flow. Okay, so and away from the surface, of course. Why do I say it is a momentum deficit? Because the velocity is zero at the plate and it keeps increasing as you go away from the plate, which means there is a deficit of momentum as you get closer and closer to the plate. So that is what we are talking about. So away from the surface, this diffusion of momentum away from the surface. Now, molecular diffusion along the flow obviously can be neglected. And that is what we've been doing, right? When we say that Reynolds number is very high, the viscous effects are very low, but the viscous effects are negligible at the large length scales, that is along the flow. So these are that molecular diffusion along the flow is negligible compared to the downstream transport of momentum. So that takes us to the discussion of, we'll talk about two different length scales here, especially in the case of a boundary layer, the diffusive and convective length scales. Now, as the equation we saw earlier, this particular equation, L over L is Re to the minus half, you can see that the boundary layer thickness is much smaller than L in which the boundary layer develops. So that small L is like a diffusive length scale because it represents the diffusion of momentum away from the surface. So that's a diffusive length scale. On the other hand, capital L represents the momentum transport along the plate. So that is like a convective length scale. So you have convective length scale versus diffusive length scale. Diffusive length scale is the small l. So this is the small l, and convective length scale is capital L. Here, it is important to understand these two length scales and where viscous effects plays an importance. So this is beautifully presented in the book of Tenikis and Lumley, where they talk about the different length scales in detail. So a lot of these kinds of flows are very slender. What do I mean by that? Their width is much smaller than their length. The boundary layer is an example of that. And if we look at this example here, I have convection and diffusion. So it is, again, this is all convection and diffusion of momentum. So you have momentum transport in the horizontal direction and in the axial direction along the flow, and you have diffusion of momentum diffusion away from the surface and in the transverse direction as indicated in this figure. So you have a small l, which is your diffusive length scale, and you have a capital L, which is a convective length scale. So these are the two length scales, right? And this wide separation between lateral and longitudinal length scales leads to a lot of different assumptions. So we know that L over capital L can be a very, very small number, especially if the Reynolds number is high, because we know now that L over capital L is Re to the minus half. So for really large Reynolds numbers, L over capital L is a very small number. So that you can make a lot of assumptions based on that fact alone, in the sense that small l over capital L is tending to 0. The whole idea of the boundary layer equations, the Prandtl boundary layer equations, came from assumptions like this, assuming that the boundary layer thickness is much smaller than that convective length scale. Although Prandtl boundary layer equations were meant for laminar boundary layers although at high Reynolds number, but still laminar boundary layer, because that was an assumption that he made. However, this asymptotic assumption was made, as in L over capital L tends to 0. So you can have these regions, have distinct characteristics, right? They are governed by the asymptotic approximation that L over capital L tends to 0, and they tend to be much simpler than the actual Navier-Stokes equations. The Prandtl boundary layer equations is an example of that. So now let's think about the turbulent boundary layer. And let's have a discussion on that. The turbulent eddies transfer momentum deficit away from the surface, we know that. And with the characteristic velocity fluctuations of the order of u, the boundary layer thickness increases at a rate, for example, this is the rate at which the boundary layer thickness is increasing, dl dt, which has to be equal to u, because as in small u, because that is the velocity scale here. Now, if you look at the flow time that it takes for one particle to go from, say, the origin of the boundary layer or the leading edge to a downstream position capital L, okay, to a downstream position capital L, you would think that time scale is of the order of magnitude of L over U, which is what is shown here. So now if I think of my diffusive length scale, small l, it can be written as U times T, and T is that time scale associated with the large length scale. So that would be UL over U. So what we now have is small l is of the order of magnitude of UL over U. Okay, so now let's think about in terms of diffusion time. So essentially what we are doing is we are equating the turbulent diffusion time L over U, this is the turbulent diffusion time, to the convective time scale L over U. So earlier we looked at the diffusive length scale to the convective length scale. Now we want to look at it in terms of time scales. So you have a diffusive time scale, which would be L over U, small l over small u. This small l is the diffusive length scale and small u is the characteristic velocity in the small scales. So then you have a convective time scale, which is capital L, which is the large length scale or the length of the plate under consideration, divided by capital U, which is of the order of magnitude of the velocity that is coming onto the plate. So you could use this for a laminar boundary layer and the same procedure, because what we are considering here is a turbulent boundary layer. Although when you consider a laminar boundary layer, your small l is now different. It is not dependent on capital L. It is dependent mostly on diffusion. So that small l increases at a rate of nu t to the half for laminar boundary layer. In a turbulent boundary layer, it is different. It increases at a rate of small u, as we had seen here. dl dt is small u, where u, small u, is of the order of magnitude of the velocity fluctuations, like an RMS velocity. Now, once we have that, we can write this time scale as L over U is of the same order of magnitude as capital L over capital U, or L over L is of the same order of magnitude as U over U. So the ratio in which you have the length scales, the diffusion to the convective length scale, is similar to the ratio of the velocity scales. The velocity scales being the diffusion, the RMS velocity to the large scale velocity. Or the time scales are different. The diffusion time scale is of the same order of magnitude as the convective time scale. Again, this is momentum diffusion. So essentially what they do is these relationships mainly relate the characteristic length scales to each other and the characteristic time scales to each other. We are just doing an order of magnitude analysis. You should not use these as a formula to calculate, say, the time scale. Okay, it is just for us to get a grasp of what the time scales are and what the length scales are. So now let's use this to estimate a very realistic quantity like friction. And we will consider both laminar and turbulent friction. So, for example, if I look at equations 15 and 16, where are 15 and 16? This is 16, where you're relating the time scales to each other, and where you're relating the length scale to the velocity scale, which is 15. 15 is this equation here, where you have the ratio of the length scale being the same order of magnitude as the Reynolds number to the minus half. So now, if I use that, I know that experimental data has always suggested that U over U is of the order of 0.01 over a wide range of Reynolds numbers. So we know that we have a rapid growth of turbulent flows because this is U over capital U, which is equal to approximately 0.01. It varies as close to RE to the negative half, isn't it? Because L over capital L is of the same order of magnitude as U over U, which is of the same order of magnitude as RE to the minus half, isn't it? Because we showed earlier that L over capital L is RE to the minus half. So U over U is also RE to the minus half. That's where we are getting this from. And now values wise, U over U is of the order of 0.01, which means over a wide range of Reynolds numbers, we see a rapid growth of Reynolds number. If we can relate this to a coefficient, we can gain a lot more understanding of this problem. If we can relate it to some kind of coefficient. And a good coefficient to relate this to would be, say, a coefficient of drag. So let's try to analyze the drag here. If I consider a laminar flow in 2D with a length L, the drag D is given by this equation. This is a simple equation. It's basically, you would have learnt in fluid mechanics that it is of the order of magnitude of rho U squared L. U, capital U being the free stream velocity, rho is of course the density, and small l is the boundary layer thickness. So the drag is of the order of magnitude of rho U squared L. We would have proved in fluid mechanics that it is actually rho U squared theta, where theta d theta dx, where theta is the momentum thickness. But again, we are saying it is of the order of magnitude of rho U squared L, since we know what L is, or we've been dealing with L. So the drag coefficient is CD, which is, this is the definition of drag coefficient, CD given by drag force divided by half rho U squared L, capital L being the length of the plate. If you substitute, use this previous equation, so D is equal to rho U squared L. If you use this from 17 and consider the drag coefficient here, you will get 2L over L, which is 2 RE to the minus half. It is 2 times RE to the minus half. So this is for a laminar boundary layer because the drag force came from that equation. For a turbulent flow, on the other hand, the mass flow deficit at the end of the plate is proportional to rho UL. So now, just like we had earlier when we showed the length scale, the diffusive length scale in a turbulent flow is related to the velocity fluctuation. In the laminar flow, it is just related to the kinematic viscosity and the time scale. In the same way, for the mass flow deficit at the end of the plate is related to rho UL, which means the momentum deficit, which is what the drag is. The momentum deficit is the loss of momentum, or the momentum deficit is proportional to rho UL times capital U. So the drag is of the order of magnitude of rho UL. There's a velocity fluctuation in there, and there's a free stream velocity also in there. So that is the drag force now. Now calculate the drag coefficient, as in the same equation. This same equation, but instead of D, put in rho UL. And then what do you get? You get 2U over U, L over L. And you know that L over L is of the same order of magnitude as capital U over U. So your drag coefficient now is 2 times U over U, the whole squared. You now have something different. Look at what you had earlier. The drag coefficient was RE to the negative half, whereas now you have small u over capital U squared. What does this mean? So experimental evidence has shown that the turbulence level, okay, meaning the ratio of velocity fluctuations to the large scale velocity or the free stream velocity, varies very slowly with Reynolds number for turbulent flows, of course, because we are talking about turbulence level, in such a way that the drag coefficient, which is given by equation 21, is actually much larger than what you see in a laminar flow. That is essentially what is shown in this figure here. I have the drag coefficient of the y-axis and I have Reynolds number on the x-axis. It is taken from Tennekes and Lumley's book. He uses a notation of R for Reynolds number, but we've been using it as Re. So Re is UL over nu, of course. And you see how the variation of drag coefficient is with laminar flow versus turbulent flow. With laminar flow, there's a significant dip in drag coefficient as the Reynolds number increases. As long as the flow is laminar, you see this huge slope. And then as it is transitioning to turbulence, you see this line that the slope is much lesser than what you would have in a laminar flow as the Reynolds number increases. I'm talking CD versus Re. Also, so that is indicative of this particular sentence where we say that the turbulence level actually varies very slowly with Reynolds number. And that is why you're seeing a line which has a slope that is much less than what you see in a laminar flow. That's one thing. The other point from this figure is that the drag coefficient is actually much larger than what you see in laminar flow. The drag coefficient in a turbulent flow is much larger than what you see in a laminar flow. And that is expected. These velocities are, this ratio here is actually compared to what you would have in a laminar flow. Like for instance, here you have it as Re to the negative half. Re to the negative half versus U over U squared. You can only guess which one is going to be higher. It is going to be U over U squared being larger. So that's the difference in terms of the drag coefficient when we compare laminar flow versus turbulent flow. And so this is now a very realistic thing. We are comparing drag between laminar flow and turbulent flow. We are pointing to a coefficient, the coefficient of drag, and showing what the difference is. This points to something that is very realistic and something that has a lot of implications in design of engineering devices. For example, aircraft wing design, automobile design. All of this has huge implications on that. We are not just looking at ratio of length scales. We are not just looking at ratio of time scales here. We are relating that to a coefficient. What does the ratio of length scale mean when you relate it to a coefficient? That is what we have done here. So here in this class, what we have done is we have looked at the length scales of turbulence. And we came up with two different length scales, the convective length scale and the diffusive length scale. When we talk about the convective length scale is the one along transport. And the diffusive length scale is one that is across the surface, and it represents the diffusion of momentum away from the surface. So again, both of this exist for laminar and turbulent flow. They do exist both for laminar and turbulent flow. It's just that the ratio is different when you have it for laminar and turbulent flow. You have these two length scales for laminar and turbulent flow. Prandtl's boundary layer equations were based exactly on this point, as in small l is much less than capital L. So that is why he was able to make assumptions and come up with a set of equations. Blasius eventually came up with a solution for that. But he assumed the flow to be laminar. So what we have done is, we have taken these two length scales and we have applied it to the turbulent flow as well. So here what has happened is, if you now look at the turbulent boundary layer and look at the rate at which that L is increasing, it is now a function of the velocity fluctuations, as opposed to in a laminar flow where L is a function of nu t, the kinematic viscosity. So that is what we have done in terms of the length scale. We have taken the diffusive length scale and the convective length scale and tried to come up with relationships that are based on the ratios of these two length scales, and even better, we related these ratios to the drag coefficient both in laminar flow and turbulent flow. In the next class, we will start to look at the small scales of turbulence. We will focus more on the small scales of turbulence, specifically as Kolmogorov came up with it and called it the inner scales or the smaller scales in turbulence, and we'll focus on that. Thank you.